I guess by now you guys know how to say mu because of what I've been doing to my soundtrack. Let's look at a couple of concrete examples to help you with the assignment. A 10 kilogram object is slid on a surface whose coefficient of friction is mu equals to 0.3. Calculate the frictional force against it. So here would be our free body diagram of the normal force up and the force of friction backwards. Now, when I say slid, I didn't specify if the situation was constant speed or not. Let's say in this case, speed is not constant because I didn't say whether it was accelerated or not. Speed is constant can be expressed in three ways by writing speed is constant, v equals constant, or a is equal to 0. So we want to do a speed is constant. Now we can use the formula. Force of friction is mu Fn. Fn will have the value of mg even though it did not originate from gravity. It's a different force that was propelled into existence by gravity. It has the value of m times g, but it is actually truly a unique force. We calculate the force of friction. With the values given, we get 29.4 newtons. Second example, the object is now accelerating. Notice the arrow now says direction of acceleration. A 20 kilogram object is accelerating at 2 meters per second squared. The surface has a coefficient of friction, mu k, is 0.3. It's a kinetic friction because it's moving. In a problem, if you just wrote mu and didn't specify k or s, I'm fine with that. We already know. The subscripts may start to make you feel, you might be going, these subscripts are just so much, it's confusing me. Then just drop it. So this person is, say, pushing the object forward. That's the applied force. There's our normal force. And we now have a force of friction that has been created from the normal force. You can calculate the force of friction easily enough, but the total force is not just the force of friction because our little guy is adding a second force. The acceleration is a result of the total or net force. The previous problem had a single force, just friction. This one, the object has got two forces on it. The man pushing an applied force and the force of friction. So net force is going to be a combination of two. And remember, F equals ma. The ma is not a new force. When you see a mass accelerating, you are watching the end result of what the force did, not where the force came from. So when we solve sum of force equals ma, that is the behavior we have seen, and that behavior showed up because of these actual forces on it. The acceleration is going to be the total force divided by mass. With the given acceleration, we can calculate the net force to begin with. So we can calculate sum of forces equals ma, and we get the total force is 40 newtons. That doesn't tell us where the 40 newtons came from. Did it come from one force? Did it come from a chain of butterflies tied to the object? Was there a frog kicking it with its legs? We now have the force that triggered the observed behavior. Now we go looking for the little pieces of that force. So we have a total force of 40 newtons, and it came from two other forces. Now, the force of friction we can calculate. The force of friction is the roughness times the weight of the object. We're getting about minus 60 newtons. So we have about a negative 60 newtons. So this guy had to push hard enough to have 40 newtons left over. Well, how hard do you have to push to counteract minus 60 and be left with positive 40. 100 newtons. Here's another example. A 20-kilogram curling stone is traveling at an initial speed of 2 meters a second. The friction of stone on ice is decimal 0.168. Calculate the net force and deceleration of the stone at the moment it is released. The second that man lets go of the curling stone, his force on the curling stone is 0. So the applied force would be the curler. And that applied force is going to be nothing at the moment of release. That's why I specified that. So all that will be left is the force of friction. The force of friction is going to calculate out to minus 3.29 newtons. That force of friction is the only force on it. So there is no applied force now. So the force of friction is responsible for the observed behavior. And when we use that now in the formula, we get an acceleration of 0.1645 meters per second squared. And I goofed and dropped the negative sign. It's slowing down. The animations came in at the wrong time. Now let's go back to pure kinematics. If the stone started at an initial speed of 2 meters a second and decelerated at 0.1645 meters per second every second, how many seconds would go by for it to stop, and how far did it travel? So we're no longer dealing with forces at all. We're back to those 5 possible equations. So I set the problem up here. I have an initial speed and an acceleration on the left and a final speed of 0, and we want the distance and the time. We have 2 unknowns in here, distance and time. So any formula that has both distance and time cannot be used because you would have 2 unknowns in the equation. So we are down to only 2 equations that are possible to use. Now I didn't put the delta V here, right? It's supposed to be there, but the deltas can sometimes confuse you. So our 2 solutions wind up looking like this. We can calculate the time by using this formula because it refers to time, rearrange, put our values in, and we get about 12 seconds. For distance, the only formula that mentions distance and does not include time is this one. We rearrange, put the numbers in, and we get 24 meters. So this curling stone takes about 12 seconds and 24 meters to stop. Are these numbers realistic? In this problem, I did not invent the speed of the curling stone or the coefficient of friction. I looked up the coefficient of friction and I looked up the average speed of a curling stone on release. If you have watched curling, does 12 seconds for the curling stone to stop seem reasonable? And yeah, I've seen a lot of curling matches and it's like 10 to 15 seconds. 24 meters, is that a reasonable stop? Well, I looked up the length of a curling sheet and they're 45 meters long. So this is half the length of a curling sheet, I think they call it. So yeah, these numbers actually seem to fit reality reasonably well, considering these were reasonable numbers. Here is what I call a minimalistic example. I'm eliminating all the diagrams and all the intermediate steps, and I'm just trying to keep it without all that, because hopefully all the diagrams help, but at the same time, they can add confusion. So we have a car at 1,850 kilograms. It's traveling at full highway speed and stops in 4 seconds. What is the friction force generated by the brakes? This example can cause what I call instant stupidity, meaning I create a question that doesn't use the new current idea and you halt, dumbfounded, because where is the mu? This is the teacher's fault and it's yours. We both together have set up a school system with expectations that whatever I'm currently teaching must have the answer to all the questions. And it's just not true. It's very common in physics, like close to 100% of students do this. If I teach you a formula on Tuesday, you suddenly think the formula on Monday doesn't count anymore. And I want to break that habit. There's a reason I'm doing this, is because I don't want students to keep being stuck in that trap, which trapped me as well. So the first thing, we don't need any dynamics to calculate the acceleration. This guy is coming from 27.7 meters a second and stopping in 4 seconds. We're all friends here. We round out. We get 7 meters per second squared stopping acceleration. Whew, that's close to 1G. That's pretty. You do realize, like, if 1G is 10, this is 70% of 1G. That would be getting close. What would 1G feel like in your car? You sit still in your car, seat belted, and a tow truck lifts your car off the ground from the rear, so you're hanging in the seat belt facing down. That's what 1G against the seat belt would feel like. This is 70% of that. That's a pretty good halt. The force generated for a car to decelerate like that, we just multiply these two numbers. I didn't put a negative in because I'm just calculating the magnitude of the force. And I get 12,950 newtons, which is best written as 13 kilonewtons. And you could go stopping or negative at that point. So, yeah, it's a pretty violent stop. That's not a normal stop. Now, here's a question. What actually stopped the car? The friction of the brakes on the brake drums or the friction of the tires on the road? Let you mull that one over for a day or two. And then we did the Spock got lost, but I'm not going to show you clip inside again. I don't show YouTube videos inside a YouTube video. But this is a hyper-focus problem. If you watch this Voyage Home clip, I really want you to. This is what happens to you sometimes. You get caught up in the details, and when someone asks you, would this hurt in a physics problem, you go like, and I want to get you past that. Now let's go back to our minimalistic example. This is what you were really expecting as a question from a teacher. An 1,850 kilogram mass traveling at 28.6 meters per second is sliding on a surface whose friction coefficient is 0.5. What will be the force of friction? And you go, oh, okay, I know how to do this one. We were just given a formula yesterday to do this one. So this is simple. I'm going to go, force of friction is mu times Fn, and I just go put in the values in the problem, boom, 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 9,065 newtons. But that's exactly what I asked you in the previous question. Just the phrasing change can leave you going, but it's not using the exact formula we were just taught. And then I ask, what deceleration would this vehicle experience? And you go, oh, I can do that now. The total force on this vehicle is only friction. And the total force is always ma. Therefore, the acceleration of this vehicle is just going to be that friction force divided by its mass. I get 4.9 meters per second squared. That's half a g. Now let's try to understand this value. If you were in this car, would you find it to be a normal braking experience or something a little bit odd? Going from approximately 30 meters a second to 0 at a deceleration of 4.9 newtons per kilogram, same as meters per second squared, this is literally 1/2 g. Given the acceleration is about 5 meters per second squared and the initial speed is about 30 meters a second, we get, by rearranging, this person's going to take about 6 seconds to stop. Does 6 seconds sound to you like a long time to brake a car, an abrupt time to brake a car? And the distance the vehicle is going to take to stop is 90 meters. Does this seem normal to you? Well, half a g in 6 seconds. I would say from my just thinking about trips I've been on, a 6-second stop from highway speed is pretty abrupt. It's not like killer abrupt, but nonetheless, you'd spill your coffee if someone did this to you. This is a pretty quick stop. Now, what about 90 meters? A car stopping in 90 meters. Well, a Honda Odyssey is 5 meters long, so this is 18 vehicle lengths. So that isn't too short, because they say you should only be about at least 10 vehicle lengths behind another car. Seems like a pretty strong braking situation, but the distance is kind of far. Well, I wonder how far it is. So I go onto Google Maps and I find my house. Okay? And I've already screen captured it onto Paint. And we look at Paint and I go, there's the size, the little map scale down here. That's 50 meters. So I'm going to drag 50 meters onto my neighborhood street. Now I can't turn it at an angle. Paint doesn't allow that. So that's about 50 meters. So I'm going to pull a little trick here. I'm going to move this up to there. And I know I can do a quick little snaggy trick here. I'm going to go like that and go. That's about 50 meters. So, that's about 50 meters right there. So that means 100 meters looks to be about from my house to about 3/4 of the way down the street to about there. So I'm going to go back to Google Maps. And I'm going to go to Street View. Thinking. Oh, come on. This is like...
Do something. Do something. Yes. I see now. Zoom.
Road Street. Meters down here. So I'm looking
mostly down that city block. So 6 seconds to stop from that speed would take me past like 1, 2, 3, 4 houses. Almost 3/4 of a town block. So that's an example of how you could, let's say your teacher next year goes like, try to make the situation real. You could capture a street view of your house and plot it out on the neighborhood street and go, see, that's what it would look like. So it's a pretty rough stop, but it does show you that even 6 seconds to come to a halt, you still travel 90 meters. That's like more than half a block. So this is why they say keep away from the vehicles in front of you. Because everybody in the car just lost a grip on their food, and you still took almost 20 vehicle lengths to come to a halt. You're rear-ending somebody. As a final note to applied physics, rock climbing is an example of lots of applied physics. I did a lot of rock climbing in university and high school. The highest building I ever climbed was the highest building I ever climbed was about 100 meters. The highest I ever climbed was about 400 meters up a cliff. The biggest problem when you're rock climbing is when you're doing this roping situation here is if you fall, the person down below is called the belayer, is supposed to stop you. Well, even a lightweight guy is still going to generate 500 newtons just hanging off the rope. If he fell and shock loads the rope, it will be much higher than that. If this person down here was just holding the rope in their bare hands, they would have their hands destroyed by friction burns. So friction is what is used to stop the person from falling. And this was the classic way of generating friction called a Munter Hitch. This causes the rope to engage in so much friction you could stop a car with a simple little knot. And if we were in school, I'd show you this. So the Munter Hitch was the classic way you could stop a falling climber. The earliest manner was just simply to wrap the rope around your body. Now what if you're rappelling, if you're sliding down the rope? Then they go to one of these two systems. The figure 8 on the left generates a huge amount of friction, and with a very tiny force on the pull down end, you can stop yourself cold. However, where does all the energy from friction go? It goes into heat.
So if you decide to rappel like some Roger Ramjet in a Wheaties commercial, you're going boing, 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 boing down the cliff really fast, that figure eight can get too hot to touch. And that actually damages the rope inside. So for people that are really rappelling a long distance or really fast, they switch to a thing called a brake bar, where the strands of rope pass through numerous friction points. So the least amount of bending on the rope is best for its survivability and long life. And the brake bar spreads the friction out so the rope does not get so hot on the way through. And you might go, well, how hot can the rope get? I saw one once where they demonstrated with the stuntman. He came down the Seattle Tower on the world's record rappels time, and he rappelled down a building like almost as big as a CN Tower in 30 seconds. And the device melted right through the rope. But it doesn't matter. You just need to get those ropes toasty. There's like 5,000 core fibers, and those tiny nylon fibers will weld together. And people that have abused the rope starts getting brittle. They're a very delicate structure. So climbing is an applied physics. And if you actually want to get licensing at levels of rock climbing, they do the physics of falling, friction, and other things. But knots themselves, the whole purpose of a knot is to generate enough friction. And so the knots have been studied for the friction they devise, and physicists have studied knots in great detail. The weaving of your clothing, if it wasn't for friction, a lot of your clothing would come apart. It's the fact that there is friction on the fibers that prevent the thing from unraveling. And this gave a big problem to making Teflon clothing, which is called Gore-Tex. Teflon itself is so low friction you can't even get color to stick to it. And so Teflon is very difficult to make clothing out of, but what you get is a clothing that has such low friction that nothing sticks to the Teflon. And so you have stain-proof clothing, but it's very difficult to work with. So we're going to look at a few applications of that. Now, one of the most important, interesting things is the human body. You have a thing called synovial fluid and cartilage. You've probably touched cartilage before if you're not a vegetarian, and you've eaten a chicken breast, and there's that white waxy material between the breasts. Next time you have a chicken breast, find that white cartilage and feel it. It is some of the slipperiest substance known. Cartilage makes up your ears and the tips of your nose. So in your joint spaces, there's a cartilage cap on the bone, and there's a fluid space in here with the discs called synovial fluid. We have not been able to replicate the low friction of those joints. And as you get older and get arthritis like me, unfortunately I'm also getting rheumatism, my immune system is attacking this buffer space, and you start to get bone-on-bone friction. And once you reach that age, or if you're an athlete and you wreck your cartilage, you'll discover missing that little slippery stuff and the oily fluid in between really minimizes your willingness to move. We have not been able to replicate that stuff. This is complete cartilage destruction of the hands due to rheumatism, and this buffer joint here is breaking down. So you can watch the videos, but if you could find for industry something that matched the synovial fluid in a human being and use that in the gearbox of your car, you'd become a billionaire. It'd be crazy effective. One of the things I find most fascinating about body lubricants is, let's say your saliva, which is slightly greasy. If Fido licks a plate clean in your kitchen and you pick it up the next day, touch the plate, it's dead dry. Oil left on a plate would be greasy, sticky, and collect dust. But I find after a dog's cleaned a plate, the plate is bone dry to the touch and not sticky or tacky at all. Start to wash it, and the second you wet the dried saliva, the plate goes to being like super oily and slippery. So saliva can dry to a non-sticky material and be back to being a lubricant the minute it's wet. Most of our lubricants, if you leave them out, they dry and harden to like a wax-like coating, or if you leave oil exposed to air, it collects dusts and becomes a real mess. So I find that the lubricants that the human body produces have really neat properties that they change their behavior according to the need. And so studying the lubricants in the human body is giving us a lot of insight into how to make better lubricants for our cars and other things. And it's a multi-billion-dollar industry. Getting rid of friction where we don't want it
is a lot of energy. Like a lot of our vehicles and stuff, about half their energy can be overcoming friction or more in the system.